Hello everyone. In this lecture I want to discuss the interference of waves. So we're starting a new unit now. We've talked a lot about traveling waves and how to describe those mathematically, but now I want to discuss this important idea of what happens when two waves encounter each other. And that's what leads to this concept of interference of waves, and then we'll also learn how to describe it mathematically, so the mathematics of wave addition. What we're going to talk about here is we're going to understand what happens when two waves encounter each other, and that's going to be the phenomenon of interference. And then we'll learn ways to add two sinusoidal waves graphically and mathematically. And we're going to focus on this particular case where the waves have the same frequency and the same amplitude. We're going to learn these terms of constructive and destructive interference and how to picture those in 2 and 3 dimensions. And we'll also learn the conditions for constructive and destructive interference. In which situations do waves add up constructively, and in which situations do they add up destructively? All right, so first thing is, what happens when two waves encounter each other? Let's take a little look at a simulation, because it's easiest to visualize it. So here I've got the simulation of a wave on a string. I've got this end free, and this end is attached to this pole. And let me just put a single pulse down this wave, or a single pulse down the string, and you can see it will travel down like this. Once it encounters this end, it will be reflected backwards because it's the free end. And then when it encounters the fixed end, it will be reflected upside down. Okay, so it looks like this. Okay, so I'm going to let this go one more time through, and then I will send another pulse down. Okay, so I'm going to send, as this one goes that way, let me now send another pulse down the string, so right about here. Okay, now the two are going to encounter each other. See if you can keep an eye on what happens. All right, so we just saw something interesting happen, and then something interesting happened again when they encountered each other. Okay, let me try to do it in slow motion so you can see exactly what's going on. Okay, here we go. Let me pause it here. Okay, we see that the amplitude of these pulses is about 1 centimeter. You can see these are lined up with the bottom of this ruler. Now let's put it in motion, and I'm going to let these two go. And watch what happens when they encounter each other. For a moment, right about here, when the two waves are completely overlapping, I've got a much bigger pulse, which is about 2 centimeters high. So it's about twice as big as it was before. And then a little bit later, right about there is about 2 centimeters. A little bit later, they have passed through each other completely as though nothing happened. So they added up for a second, and then they passed through each other unaffected. Let's see what happens when they're passing through each other here, where one is upside down compared to the other one. You can see that for a moment, if I can get there, right about here, they're basically canceling each other out. So those two are canceling each other out. I have basically a flat string at this moment, and then a few moments later, they have passed through each other, and everything continues. Okay? So this interesting thing happens with waves where they add up, they pass through each other for a moment, forming a bigger pulse or canceling each other out, and then they pass through unaffected. So this is called the superposition principle. When the two waves encounter each other, they add together point by point, and I'll have a little more to say about exactly what I mean by that. They pass through each other without being affected, and this is a wave behavior. It's not the way that particles behave. For example, if you throw two baseballs at each other, they don't suddenly overlap and form a bigger baseball and then pass through each other. Okay, so waves are different than particles, and this kind of interference of waves is one thing that distinguishes them from particles. Let's focus now on a particular case. I just showed this pulses adding up, but let's talk about what happens if you add two waves together which have the same amplitude, the same frequency, but a different phase. Okay, and then later on we'll learn how to add together sinusoidal waves which have the same amplitude but different frequencies. And then the general case, which has different amplitudes and different frequencies, is going to be more advanced courses. So what we're going to focus on now is two waves. They have the same amplitude, they have the same frequency, but they're not, they could be shifted relative to each other. So there could be a phase difference between the two waves. What happens when they add up or they encounter each other? Before I show you the general case, we're going to talk about two specific cases. So if the two waves are completely in phase, so if they completely overlap, then the resulting amplitude is twice the amplitude of one wave. So this is a little bit hard to see. There's two waves here. One is blue, and then there's another one you can imagine is right behind it, which is exactly the same amplitude and phase. And then when I add those two together, I get the brown one, which is the sum of the two. This is called constructive interference. So the two waves are completely overlapping and completely adding up. Okay? By this I mean that the phase difference between the waves is 0 degrees. So both of the waves are completely lining up, and then I get constructive interference. When the two cancel out, that's when the waves are like sort of opposite to each other. So now you can kind of see the two waves. There's one blue one, which is called Y1, and one green one, which is called Y2. And you can see that everywhere the two waves are opposite to each other. So when I add them together, I end up with nothing. So this is what we call destructive interference. This happens when the two waves are completely out of phase. The phase difference between the two waves is 180 degrees. Okay, so one wave is 180 degrees out of phase compared to the other one. So you have these special cases. Constructive interference, that's where the two waves are in phase. They totally overlap and add up. And then where they're completely out of phase, they're canceling each other out, and this is called destructive interference. You could have something in between. You could have something which is neither constructive nor destructive. You know, there's some phase difference between them. In this case, what's shown here is the phase difference between the waves is 60 degrees. So it's not perfectly destructive interference, and it's not perfectly constructive interference. And you can see that the red line, which is the sum of the blue and the green, is not totally adding up. It's not twice the amplitude of the original ones, and it's not totally canceled out either. So it's not perfect constructive nor perfect destructive interference. Okay. Let's try to learn a quick way of doing this graphically. So suppose I've got two waves, the red one and the blue one, and I want to figure out what is the sum of these two. So I want to figure out if I add these two together, what wave do I get? What I mean by superposition principle is each point is found by adding the 2 points on the two waves. So if I want to know where the sum of these two is, like suppose I want to know where the total wave is at this point, let's say here. I want to know where's the sum of those two. I need to take the value of the red wave and the value of the blue wave and add those two together. That tells me the total sum of the two. So I basically take every point, add the two values of the two waves together, and then that gives me my new wave. Right? Now, you can kind of see how this is going to work fairly straightforwardly. So there's a couple special points where it's pretty obvious how to do this. So for example, at these black dots, like this dot here, the blue wave has some value, which is a little bit less than 1. And the red wave is crossing the axis. So the red wave is 0. So that means the sum of those two is going to be the value of the blue wave plus 0, because that's the value of the red wave. And so this black dot is going to be the sum of those two. It's just equal to the blue value because the red one is 0. And here the red one is something, and the blue one is 0. So the sum is going to be that there, right? So I labeled all those points with dots. It's pretty easy to label those points. Just find out where one wave crosses the x-axis, and then your black dot is going to be on the line of the other wave. Okay? And there's a couple where it's pretty obvious, like what about where the two waves cross, like here? That means the two waves have the same value, so the sum of them is just twice that value. So if I look roughly at this point here, it's a little bit above 0.5, so maybe it's about 0.6. So the sum of those two because they each have the same value of 0.6 there. I just have to take 0.6 times 2, and I'm going to end up with something around 1.2, and so I have this black dot here. And then I did the same thing with a bunch of other ones here. Already you can kind of see what's going on. You're starting to see this shape here. So like there's a sine curve which is emerging, right? So the sum of the two waves is also a sine wave, which you can kind of see here. There's one other point you can find where they completely cancel out. So that's those dots there. And then you can connect all of them, and you see that the sum of those two waves, which have the same amplitude and the same frequency, but a different phase, is another sine wave with a different amplitude and a different phase. Maybe to make that a little more clear, let me try to put some animation with it. Okay, so here is basically that same idea. I've got two waves which are red and blue, which are, you can't see the red one because they totally lie on top of each other. And then the black one is the sum of those two. So I've just got some code here which does the addition for me. And I've got a knob here which is phi, the phase difference of the wave. So I'm going to shift one of the waves relative to each other, relative to the other one. Right now phi is 0, so they're in phase, and you have constructive interference. Let me try to shift it slowly. Okay, what you see happening is the blue wave is being shifted relative to the red wave. You see, like, this is the value of the phase difference between the two waves. So I've got one wave which is shifted by minus 0.76 radians compared to the other one, and I'm using the black line as the sum of the two. So let me keep going. You can see, like, keep going. I'm seeing that the amplitude is decreasing for the black wave. And right around, getting there, right around here, I'm starting to get the two completely canceling each other out. So this is the destructive interference. And you'll notice that the phase difference between the waves is pretty close to pi, right? 3.13. So it's not exactly canceled out, but if it was pi, they would be exactly canceled out. Now if I let it go a little bit further, it's going to come back again. So then they're starting to add up again, coming back into phase. And then once I've shifted it by 2 pi, I will be back at constructive interference again. So you can see, like, depending on the phase shift, I have constructive interference, destructive interference, or something in between. Right about here is 2 pi, pretty close to 2 pi. I've got back to destructive interference. So we've talked about how to do this graphically, just by taking the value of each wave at each point and adding it to the value of the wave at the same point, and then just adding those two together. That gives me the value of the combined wave. Let's show how to do it with equations. So we know how to describe each wave mathematically. We know that each one is a sine kx minus omega t, a standard wave equation. So we need to learn how to add two sine waves together mathematically. I'm going to start with this thing that seems to come out of nowhere. These are angle addition formulas. So it tells you how to add, if I have sine of a plus b or a minus b, cosine a plus b, cosine a minus b, I can use these formulas to add angles together. Now, I'm not going to show how to do this, but basically you start here and you do some algebra, and you end up with the following identity. So this identity, there's nothing mysterious about it. It's just, it comes from these trig identities and doing algebra on those. Sine of a plus sine of b, so that's the sum of two sine waves, is the product of a cosine and a sine. So cosine a minus b over 2, sine a plus b over 2 with a 2 out in front. Okay. So this is a way you can add two sine waves together by using this formula. So we're going to do this. Let's try to add two waves together. So let's say here is wave 1. Let's call it y1 of x and t. It has amplitude a, wavelength, wave number k, frequency omega, and phase phi. And then I've got another one here, which is y2 of x and t, which has the same amplitude, the same frequency, but a different phase. In fact, this one has 0 phase. Okay? So the only difference between these two waves is that one has a phase shift and the other doesn't. So there's a phase difference between these two waves. They have the same amplitude and the same frequency. So all I have to do is use this same formula above here. But the little a, is going to be all of this stuff, kx minus omega t plus phi, and b is going to be all of this stuff, okay? Kx minus omega t. So it's pretty straightforward. I just have to plug in to that formula. I'm going to have, what is the sum of these? y1 plus y2. It's going to be, there's going to be an a out in front, right? And then I'm going to have a 2, and that's that 2. And then I'm going to have cosine of a minus b over 2. So what's a minus b? A minus b is phi over 2. Because a and b are the same, except the only difference between them is this, right? And then I'm going to have sine of a plus b over 2. So what is a plus b? A plus b is kx minus omega t plus phi plus kx minus omega t, whole thing divided by 2. And you can simplify that a little bit, which I'll do on the next slide. Okay, so when you do this, you simplify it, you end up with this formula. So that's the formula for the sum of two waves with the same amplitude, the same frequency, but a phase shift of phi between them. Let's try to think a little bit about what this formula means. So here's what we just did. We said we have two waves here, same amplitude, same frequency, different of phase between the two. And then when you add those two using those trig identities, you get this formula here. So when you add these two, what is the shape of the wave y1 plus y2? Here are your choices. So is it a sinusoidal wave with amplitude A, with amplitude 2A, something other than a sine wave, or a sine wave with amplitude 2A cosine of phi over 2? Go ahead and pause the video. See if you can wager a guess about this question before going forward. So hopefully you have decided on one of these. The thing that throws students off here is the fact that there's a cosine and a sine. So they kind of think that this is something more complicated. But we already saw back here, graphically, right? When I added these two sine waves together, I got another sine wave. So it is, in fact, just another sine wave. How do I see that from this formula? You see, all of this here is the thing which oscillates in space and time. That's the wave equation. And all of this stuff out here is a constant. A is a constant, phi is a constant. So I have all of the stuff out in front is a constant. Now the constant happens to involve a trig function, but it's still a constant, okay? And that means that it's still a sine wave, and the amplitude of the sine wave is this 2a cosine phi over 2. So in other words, how do I figure out the amplitude of something? It's the thing in front of the trig function, which changes in space and time. And the amplitude in this case is 2a cosine of phi over 2. So that's the important conclusion. The sum of two sine waves is another sine wave with a different amplitude, and the amplitude depends on whether those two are in phase or out of phase. Okay, so let's take a look again at this. So this is basically the same formula as the previous slide. I have two waves, same amplitude, same frequency. There's a phase difference between the two, which I'm calling delta phi on this slide. And when I add these two together, I have this formula. And we said that this thing here is the amplitude of that new wave. Okay? So where is this new amplitude equal to 2a? So in other words, if this cosine is equal to 1 or minus 1, then I've got constructive interference, right? Because that means that the original waves had amplitude A. If I ended up with another wave which had amplitude 2a, they completely added up. all right? So when does that happen? When is cosine of delta phi over 2 equal to plus or minus 1? This would be constructive interference. Well, cosine is equal to plus or minus 1 when the argument inside is equal to 0 or pi or 2 pi or 3 pi and so on, right? So if delta phi over 2 is equal to 0, pi, 2 pi, 3 pi, I have constructive interference. But then if I take this 2 on the other side, so multiply everything by 2, I see that delta phi is going to be equal to 0, 2 pi, 4 pi, 6 pi, all the even numbers. So constructive interference occurs when the two waves are completely in phase, when delta phi is 0, or when delta phi is 2 pi, or when delta phi is 4 pi, and so on. That's what we saw from the simulation, but we're seeing it here mathematically, right? Now, when does destructive interference occur? Destructive interference will occur when this amplitude is 0, right? So when is the cosine equal to 0? So destructive occurs if cosine of delta phi over 2 is equal to 0. And when is the cosine equal to 0? When the thing inside, delta phi over 2, is equal to pi over 2, or 3 pi over 2, or 5 pi over 2, so on. Okay. And then do the same thing, take this 2, well, I just cancel out all the 2's, right? So destructive interference will occur when the phase between the two waves, phase difference between the two waves is pi, 3 pi, 5 pi, so on. Odd numbers. So we've seen it both graphically and mathematically how to think about where the constructive interference occurs and when the destructive interference occurs. Okay, let's think about this question. Two loudspeakers emit sound waves with same wavelength and same amplitude. The waves are shown displaced for clarity, but let's assume that they're like completely overlapping. So I can't draw it, it gets a little confusing if I put them right on top of each other, but just assume that these two waves are going to be right on top of each other. At the point where the dot is, what kind of interference do I have? Constructive, destructive, something between, or is there not enough information to tell? I'll give you a moment to see if you can think about this one. Okay, so it's a little hard to do. I'm going to help you out a little bit. Let me put a grid on here. So I now have a grid which helps you kind of line up things. And does that help? So pause the video, see if you can decide on which one it is. Okay, the answer here is C. It's somewhere in between constructive and destructive. And you can tell because, you see, at this point where this vertical black line is, the wave from speaker 1 is at 0. So it's like halfway between its max and its min. But the wave from speaker 2 is at its maximum. So these two waves are basically pi over 2 out of phase. They're not completely opposite to each other, and they're not completely overlapping. So that's somewhere between constructive and destructive interference. How do I relate the distance between these two speakers to the phase difference? So for example, let's say I've got one speaker here with one wave and then another wave here. And let's say the two have the same wavelength and the same amplitude, so lambda is 2 meters. If these two speakers, if the waves leave the two speakers in phase, so you can see they both are coming out going down, and the speakers are separated by one wavelength, which is the case that I have here, right? So this one here has traveled one extra wavelength, and then after that they look exactly the same. So if I shift one of them by one wavelength, that's a phase shift of 2 pi. So in other words, what I'm trying to do on this slide is to relate the phase shift to the wavelength. Okay. So if the waves leave the speakers in phase, and if the speakers were separated by one wavelength, which is what's shown here, the waves would be completely overlapping. You can see that over here they're totally on top of each other, totally lining up, and you would get constructive interference. Okay. And the same would be true if I shifted it 2 wavelengths relative to the top one, 2 wavelengths relative to the bottom, or 3 wavelengths, or 4 wavelengths. What if I had it by half a wavelength? So if I shifted this one by half a wavelength compared to the bottom, so you can see that this extra distance here is half a wavelength compared to the bottom one. And so now the two are completely opposite from each other. You can see where one of them is at a maximum, the other's at a minimum. So this is destructive interference between the 2 waves. So if the waves were in phase when they left the speakers, and they were separated by half a wavelength, or half a wavelength plus 1, which is 3/2 wavelengths, or half a wavelength plus 2 wavelengths, which is 5/2, the waves would destructively interfere. Here's the general relationship between the wavelength, or the difference between the distance traveled and the phase shift. So the phase shift between the 2 waves, delta phi, is 2 pi times the distance, the path length difference here. So this is the difference in distances traveled by the 2 waves divided by lambda. So as an example, if one of them travels 1 wavelength longer than the other one, I would have constructive interference because delta phi would be equal to 2 pi. If one of them travels half a wavelength longer than the other one, then delta phi would be equal to pi, and I would have destructive interference. This can lead to really interesting things when you start thinking about waves traveling in 2 or 3 dimensions, like in water or sound waves. So let me try to show you a nice video which illustrates this.
I've got a demonstration here on a little pond where we can see this with water waves. I have 2 sources of ripples, which are basically like the 2 slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the 2 sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs.
So you can see here, that's where I'm getting a bigger wave. I'm getting constructive interference here. And that's where the wave from one of these sources has traveled 1 wavelength or 2 wavelengths or 3 wavelengths further than the wave from the other source.
The amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference, and there's basically no wave there.
So right on these lines, which is highlighted in the video, you can see that that's where I'm having destructive interference, where the difference in path length from one of these sources compared to the other is a half of a wavelength, or 3/2 of a wavelength, or 5/2 of a wavelength, so on. There's a nice applet which there's a link to here, which you can play around with, which has sound waves, and you can see where the constructive interference occurs and where the destructive interference occurs. So this is that same idea, but just like sort of a little bit more straightforwardly presented. So let's say I've got 2 waves, like these could be speakers here. And if you're located here, the distance that one of the waves has traveled to you is r1, and the distance that the other wave has traveled to you is r2. If I'm located right in the middle of those two, the r1 and r2 are the same, so those 2 waves will be in phase. And you can see, if you look carefully here, that these 2 are lining up, those 2 waves. They're in phase. If, on the other hand, if I'm over here, at some other point, R2, the distance r2 is longer than the distance r1, but maybe its extra distance is 1 wavelength, which you can kind of see if you look carefully down here. So if r2 has traveled 1 extra wavelength, then these two are still going to line up when they reach that point. And then, of course, here's the destructive interference case. If r2 is 1/2 a wavelength longer than r1, then when they get to this point over here, they're going to be canceling each other out, and I have destructive interference. Okay. Here, like if these are speakers, there are going to be places where there are two speakers playing the same sound at the same amplitude. If there's going to be places where you hear a loud noise, which is here, and there's going to be places where you hear hardly anything, which is where you have destructive interference. By the way, this is the way noise-canceling headphones work, is you have some sound coming into your ear, and the headphones are producing kind of opposite wave of that sound, so that when they both hit your ear at the same time, they're out of phase and they partially cancel each other out. So I think this is what I've already kind of illustrated to you, that if you assume that two waves leave their respective sources in phase and they travel different distances to an observer, we've said that I'm going to have destructive interference if the phase difference is pi, or 3 pi, or 5 pi, and so on, right? And since we know the relationship between the phase difference and the path length difference, I can tell you if the difference between the two paths is 1/2 a wavelength, or 3/2 of a wavelength, or 5/2 of a wavelength, I get destructive interference. And if it's the difference in path lengths between the two is 1 wavelength, or 2 wavelengths, or 3 wavelengths, I get constructive interference. Okay, so this one here occurs when this is equal to lambda, or 2 lambda, or 3 lambda, so on. This one here occurs when it's equal to lambda over 2, or 3 lambda over 2. The odd numbers are on the top. 5 lambda over 2, so on. Okay. Let's try to end with this example. So it's basically an example involving that exact situation of two speakers placed 3 meters apart, broadcasting the same tone. The waves leave the speakers in phase. A listener is originally located at point O, located 8 meters from the center line. The listener then moves to point P, so upwards to this point P, which is a perpendicular distance 0.350 meters from O. And for the first time, she hears no sound. What is the frequency of the sound? Go ahead and pause the video and get started, and maybe you can try to work this problem out yourself. Then we'll do it together. Okay, so let's think about what's going on here. When the observer is at point O, that's directly in between the two speakers. So at point O, R1, the distance that the sound has traveled from speaker 1, is equal to R2, the distance that the sound has traveled from speaker 2. And so this is going to be constructive interference, right? Phi is equal to 0. There's no phase difference between the two, and there's no path length difference. R2 minus R1 is equal to 0. Okay. Now, when she starts moving up from point O to point P, so moving up this way, as she starts doing that, R2 becomes longer than R1. She's moving further away from speaker 2 than speaker 1. And then at some point, she stops hearing any sound. So that's where I'm getting destructive interference for the first time. So at point P, I have destructive interference because she hears no sound, right? Destructive interference. Which means that delta phi is equal to pi. It's the first time she hears destructive interference. And it means that R2 minus R1, the path length difference is 1/2 of a wavelength. If she continued walking, she would eventually reach a point of constructive interference again, where the path length difference is equal to lambda. And then if she kept walking, she would hear destructive again, and then constructive, and then destructive. Okay. So that's the basic idea. I know that the phase difference between the waves at point P must be equal to pi, and that means the path length difference between R1 and R2 is lambda over 2. Let's try to put some more quantitative detail with it. I'm trying to find what is the frequency of the sound. So V is equal to F lambda. And since these are sound waves, I know V. This is the speed of sound, roughly 340 meters per second. Okay. And okay, I don't know what lambda is, but I do know that based on the geometry of the situation, that R2 minus R1 is equal to lambda over 2. Okay? And lambda is V over F, so this is going to be V over F times 2. Okay? This is at point P. So I can solve this for F. F is equal to V over 2 times R2 minus R1. I don't need the absolute values because I know R2 is longer than R1, just by eye. Right? Okay, now the hard part is I have to figure out what is R1 and what is R2, but that's not too hard. So I can just look at these triangles. So here's the triangle, which I can use to determine R1. And then here's another triangle, which I can use to determine R2. Okay. All right, so let me just write these things down. By geometry, R1 is going to be equal to the square root of 8 meters squared plus 1.15 meters squared. Right? So that's from the blue triangle. And R2 is going to be similarly 8 meters squared plus 1.85 meters squared. So I'll take these two things and just substitute them in here, and then I can get my frequency. So F is going to be equal to 340 meters per second divided by 2 times R2 minus R1. So I got to write all these things in here very carefully. R2 is 8 meters squared plus 1.85 meters squared, minus R1, which is 8 meters squared, plus 1.15 meters squared. Just like that. Okay. And when I plug in all the numbers, I got 1319 hertz. So take a step back. What did we use? We used V equals F lambda. V is the speed of sound. I'm trying to find F. I don't know lambda, but I can figure it out because I know that at the point P, she's hearing destructive interference. And that means that R2 is half a wavelength longer than R1. Because I can figure out R2 and R1 from geometry, that means I can figure out the wavelength, and that helps me solve the problem. To finish, let's do this clicker question. Two speakers are broadcasting a single tone in phase. The distance between the speakers is exactly equal to 3 wavelengths. What is heard at the point P? Constructive interference, destructive, cannot be determined. Go ahead and pause the video, see if you can come up with your best guess on this one. So hopefully you have voted one of these choices. I'm trying to trick you. It's a trick question. The answer is it cannot be determined. How do I determine if it's constructive or destructive? What I need to know is how much longer is B than A. If B is 1 wavelength longer than A, then it's constructive. If B is half a wavelength longer than A, it's destructive. If B is 2 wavelengths longer than A, it's constructive. You get the idea. But the only thing I've given you here is the distance between the speakers. So I know the distance between the speakers is 3 wavelengths, but that doesn't tell me anything, right? I really need to know the length A and B, and I don't have any information about that. So it can't be determined. Let me summarize. We've talked today about what happens when waves encounter each other. They add up point by point, so the net combined wave is found by adding the value of one wave plus the value of the other wave. That's called the superposition principle. When two waves travel different distances to get to an observer, they'll have a phase difference between them. And the path lengths are related to the phase difference by this equation. So if the extra distance is one wavelength, they're 2 pi out of phase. If the extra distance is half a wavelength, they're pi out of phase. Say I get the idea. We learned how to add waves graphically using that, that trick of just picking special points when I have the two sine waves. And we also learned how to add them mathematically. So if I have two sine waves with the same amplitude and the same frequency and a phase difference between them, I can use this formula. The new amplitude is found here, right? The old amplitude, 2 times the old amplitude times cosine delta phi over 2. So if delta phi is 0, I have constructive interference. If delta phi is pi, I have destructive interference, and so on. So I hope you found this lecture useful. I recommend playing around with some of those links that I posted on D2L in order to get an intuitive sense of this idea of wave interference. And then I will see you all in class, and bye for now.